Stuff look familiar to anybody? These were picked up after the exam last evening. And for the few of you who did the exam yesterday afternoon, I got your papers. Should you wish to get them back, see me right after I talk. After our talk. But the score is up for exam 2 tomorrow. How was exam 2? Chemistry's hard. Exam 1, 13 points a pop per question. Exam 2, 16 points a pop per question. We'll keep going up. The material keeps piling on. Now, thermodynamics, which guess what is all we've done so far, which is just about all you did in 2045. We've talked in brief about thermodynamics previously, to the extent of reminding you that. 2 general ways by which reaction progress can be studied, and that's what chemists do more often than anything else. Run reactions and study their progress. If we're concerned about the pathway by which the reaction proceeds and how fast it proceeds, that's kinetics. A difficult and detailed area of chemistry. Very important. But something we can't do a whole lot with, even in undergraduate chemistry, regardless of the course. So for the most part in undergraduate chemistry, particularly in the first year, we focus on studying reaction progress from a thermodynamic standpoint, which is eminently available to us. You can do marvelously accurate, sharp, clear, penetrating thermodynamic analyses of systems with test tubes, beakers, vials, nothing fancy, because you're never concerned about the time factor. And this is what you do, for example, in 46 laboratory. You did a lot of this in 45 laboratory. And again, chapter 17, 18, 19, all we've done is thermodynamics. But now we're going to look at thermodynamics by adding some new language, some of which you learned in 2045, although you should have learned all of it. Because in 2045, you did a chapter on thermochemistry, didn't you? Where you studied Q, small q, abbreviational reference to heat, which related to delta H, didn't it? Change in enthalpy. There's one major problem with looking at thermodynamics from just a change in enthalpy standpoint. What we want to know more than anything else about a reaction under the conditions under which the reaction is being studied is whether or not it can go. And you can't answer that from a delta H standpoint. You need to add to the delta H standpoint delta S, change in entropy. So we'll say a few things specifically about entropy and change in entropy today. This is the part that the textbooks leave out. It's very unfortunate. Because then they go on to do in that first semester things like analyses of phase diagrams. You did that, didn't you? You looked at water phase diagram for water, didn't you, in 2045? A phase diagram is a free energy diagram. How in the hell can you understand a phase diagram if you haven't been introduced to free energy? I don't know what these textbooks expect. Solution formation. How can you know if a solution is going to form without looking at the possibility of forming the solution from a spontaneous standpoint? That's what means whether or not the solution can form and relates to concentrations. And the criterion for spontaneous is change in free energy. All of this was imagined way back in the early 1900s, if my time frame is correct. Maybe it was late 1800s. By Josiah Willard Gibbs, who wrote this: free energy the energy available, in this case from a substance, is equal to a measure of the bond strengths, the structural integrity of the substance, its enthalpy, less this part of the puzzle. You can refer to this as the unavailable energy. Because when you multiply entropy and its units times temperature, you get energy. This is an energy equation. Now, what Josiah Willard Gibbs recognized is this is determinable on an absolute basis. Because the third law of thermodynamics says, in essence, that the entropy of a perfect crystal at absolute zero is zero. Because it exists in only one possible structural state. And entropy, arithmetically, is a log term. What's the log of 1? 0. That's where that comes from. Now, that's of no real consequence to us from an analysis standpoint at this stage of the game. But it does remind us, or bring us to the fact that you cannot measure enthalpy for a substance on an absolute basis. At least not in any fashion which is, as far as I know, known. Which means you can't measure this for a substance on an absolute basis. But what can you measure? You can measure changes in enthalpy. You did this in 2045 in the thermochemistry chapter. Just like you can measure changes in entropy. Multiply times the temperature in degrees Kelvin at which the change is observed. And when you combine the change in enthalpy with the change in entropy multiplied by this temperature in Kelvin, you get the change in free energy. Which means you can calculate for a chemical system like a reaction the amount of usable energy you can get from this process. And if you study the process under a specific set of conditions known as standard state, that's what the superscript 0 designates. You should have heard about that in 2045 lecture. And if you paid attention to what we asked you to pay attention to in 2045 laboratory, I know you heard about this, didn't you? You remember reading assignment 7 in the 2045 lab manual on solutions? Where I purposely wrote a discussion premised on the possibility of forming solutions spontaneously under standard state conditions. Anybody remember that? I will tell you right now. If you still got your 45L lab book, go back to assignment 7 and read that discussion. It is immediately relevant to what we are now considering. More on standard state later. But as I said, what we really want to know from a thermodynamic standpoint about a reaction is, can it or can it not proceed under the conditions at which it's being studied? Now keep this in mind. Just because a reaction is thermodynamically spontaneous, that doesn't mean it goes. It means it can go. Example. See this stuff? Stable in this air, isn't it? Because it's here. And ever so obviously it's not going anyplace. At least not at any rate which we can detect by eyeball observation. Is this stuff stable in air thermodynamically? The answer is no. Is gasoline stable in air thermodynamically? The answer is no. If you take information from the thermodynamic properties data table, which we're going to use extensively at the end of chapter 20 in the notes. And use that information to calculate the standard change in free energy for the reaction of cellulose, wood fiber, with oxygen from the air to make what products? What products? What products? I'm listening.
Carbon dioxide and water.
Carbon dioxide and water. You didn't hear about that in 2045? You'll find out that this reaction is, number one, highly exothermic. You know that. If you get this stuff started to burn by putting a lit match to the tail end, you got to keep adding lit matches? When you get the logs burning in the fireplace, do you have to keep throwing in heat source? Or does it go on its own after you get it started? Goes on its own, isn't it? Can it be used to heat the house? Can you roast hot dogs over the burning wood in the fireplace? Is that transformation exothermic? You're damn right. Which means it's favorable from a change in enthalpy standpoint. And it's also highly favorable from a change in entropy standpoint. You're taking a solid and turning it into vapor phase products. Does it seem reasonable to you? If entropy is from a very practical standpoint considered as a measure of the ability of a substance to distribute its internal energy, in which phase can a substance most effectively distribute its internal energy? When it's in a solid state, when its particles are locked in place, and the only mode of motion available to them is vibration? Or when it's a liquid and clearly now can move? Or when it's a gas and can move this way as well as this way and this way and this way and this way and this way? In which phase is a substance of highest entropy? Which phase? Yes, you betcha. Which gives you a practical understanding of why the combination of cellulose with oxygen to give you vapor phase products, hey, it proceeds not only exothermically, which means it's driven by a favorable change in enthalpy, it's also driven by a very favorable change in entropy. Not stable in the presence of air, thermodynamically. Why is it stable? Because the rate of conversion at normal lab conditions, or basically 25 centigrade, 1 atmosphere, is so slow that practically speaking it doesn't go at all. But you can change these conditions by striking the match, flicking the Bic. A little heat here. Get started. And after it gets started, then it will feed itself its own what? Kinetic energy requirement to keep going. What's the kinetic energy requirement that must be met for a reaction to keep going from a kinetic standpoint? It's called activation energy. Remember that? The problem with this under these conditions is you don't have any supplication of activation energy. But you get this hot enough and get it started, it'll feed itself its own activation energy because it's an exothermic process, and away she will go. So let's take another look at this consideration. Water solid, water liquid at NLC. Remember, NLC is essentially 25 degrees centigrade, 1 atmosphere. If I bring some ice cubes in here and set them on the bench top, will this go? Is it spontaneous? Is it going? Then it's spontaneous. We didn't do anything except bring it in here. How about this at NLC? Is it spontaneous? At NLC, is there anything we can do to make this spontaneous? Can we make this happen at NLC? Now you should know the answer to this because you studied phase diagram for water. If NLC temperature condition is 25 centigrade, can I get water to freeze at 25 centigrade? Is there a way to get water to freeze at 25 centigrade? Can't do it. Got your notes? Look on the second page of chapter 21. I think it's the second page. Ah, yes, it's the second page. What do you see on the second page of chapter 21?
Phase diagram.
Phase diagram for water. Take a look at that diagram. Does it tell you that it is possible to freeze water at 25 centigrade? Yes or no? No. Nothing can be done to make this process spontaneous at these conditions. Now, how about water liquid to water vapor at normal lab conditions? Or how about water vapor to water liquid at normal lab conditions? Can either of these processes be spontaneous at NLC? H2O. Wonderful stuff. Now, unfortunately, I forgot to put my water today in a beaker so you could see the meniscus level. The meniscus level is about here, at the bottom of the body proper of my periodic table on my cup. If I make a mark here to designate the meniscus level and leave the cup stand there until Monday and come back and look at the contents of the cup on Monday, will the meniscus level be the same? Will the meniscus level be higher? Will the meniscus level be lower? Well, that's the only remaining choice. Why will the meniscus level be lower? Because of evaporation. Which means, in this room, water liquid going to water vapor is spontaneous. Why is it spontaneous in this room? Water liquid to water vapor. Why is the evaporation of water liquid spontaneous in this room? What would the conditions be in this room if water liquid to water vapor was not spontaneous? What would the conditions be from a weather standpoint?
100%.
What would it be?
100%.
100% relative humidity. Would we be happy and comfortable under these conditions?
No.
Why not? Temperature would be the same.
Our sweat wouldn't evaporate.
Because as we perspire, natural human respiratory function, we would sit about and uncomfortably stew in our own juices. Because there would be no net evaporation of water liquid from our body surface, sweat. Because at 100% relative humidity, the air atmosphere is saturated with water vapor. It is not capable of absorbing any more water into the vapor phase under these conditions. But our air conditioner system does two functions. What are the two functions of an air conditioning system? Keep the temperature at levels at which we human critters are comfortable. That's usually about 23 centigrade. About 72 Fahrenheit, 73 Fahrenheit, something like that. And what else? We just implicitly referred to it. Do what? Keep the relative humidity at about 65%. Well, as long as the relative humidity is less than 100%, that process in that environment is spontaneous. Well, if this is spontaneous in this room, then is this spontaneous in this room? If this is spontaneous in this room, under these conditions, is this spontaneous in this room under these conditions? No. What will we have to do to make this spontaneous in this room? Well, we could lower the temperature. until we get to what's called a dew point. You heard that by the weather people? Dew point. Or, if we want to keep the temperature the same, then we're going to have to introduce into this room water vapor at a partial pressure which exceeds what value? Uh-oh. Back to chapter 21. I told you to look at the phase diagram. Now look one page past the phase diagram. Not one page, you got to turn one more page. Turn another page. And you'll see a table. You see this vapor pressure data table? You see that? What is vapor pressure? Certainly you talked about that in 2045. What does vapor pressure mean? What does vapor pressure measure? Louder.
Tendency of the liquid to evaporate.
Doesn't have to be a liquid. The tendency of a condensed phase to evaporate. Liquid or solid. Both liquids and solids have vapor pressures. Gases don't have vapor pressures, they're vapors. So look at this data table. What's this page? 21.5? Look on page 21.5. If the temperature in this room is 23 centigrade, well, let's make it easy. Let's say it's 25 centigrade. I know it's not quite that warm, but just to use the data table easier, let's say the temperature in here is 25 centigrade. At 25 centigrade, what is the vapor pressure of water liquid? Look at the table. Somebody holler out the value.
23.8 torrs.
23.8 torr. So 23.8 divided by 760 tells you what fraction of an atmosphere the vapor pressure of water liquid is in this room right here and now. 23.8 torr. So if I were to introduce into this room a source of water vapor with the partial pressure of the water vapor being greater than 23.8 torr, that would go. That would be spontaneous, because what dictates the directionality of this transformation or this transformation is tendency to evaporate, which means vapor pressure of the condensed phase, versus the concentration of the vapor phase. And concentration of vapor phase is most commonly measured by we just told you what it is. You read about this in chapter 17. The most common way to measure concentration of vapor phase is what? Partial pressure. So if this property of this phase of water exceeds this property of this phase of water, this goes this way. But if this property, tendency to evaporate, of water liquid exceeds this property of the vapor phase, it goes that way. And if these properties are equal, what condition exists? 100% relative humidity. Equilibrium. Now, as we have restated, the problem with the textbook thermochemistry chapter is it doesn't give you a handle on spontaneous, because these properties of a reaction system are not a criterion for thermodynamic spontaneity. Look at this process. Again, if I bring a sample of ice cubes out here, will they melt? You're damn right. And while they melt, there'll also be evaporation. So conversion of water solid to water liquid and water solid to water vapor will be taking place right here in this room if I put ice cubes here in this room. Well, if it's happening, then it's spontaneous. Is this process driven by a favorable change in enthalpy? Well, let me ask you a question. The answer to which I hope you learned about in 2045. When you measure change in enthalpy for a reaction, what do you find out about the reaction products versus the reactants? What do you find out? If you measure change in enthalpy for a reaction, what do you find out about the reaction products versus the reactants? What do you find out?
Stability.
What do you find out? Which is arguably the most important property of the reaction system from a change in enthalpy standpoint. What do you find out? Well, let's put it this way. If the reaction is exothermic, that's energy liberating, heat energy liberating. What have you found out about the products versus the reactants? What is that? Well, be careful about this. Will the products, if the reaction is exothermic, will the products have stronger bonds or weaker bonds than the reactants? Stronger. Ha ha. Their bond energies are higher. They're more stable from a bond strength standpoint. That's why this process is exothermic. When you go from less stable to more stable by increasing bond strengths, or by increasing the number of bonds in the system, or by both, you're looking at an exo process because it corresponds to increasing stability. Conversely, if the products are less stable than the reactants from a bond strength standpoint, you've got to put energy into the system to make that happen. That's endo. So back to this process. Water solid becomes water liquid, which is spontaneous right here in this room if I were to bring ice cubes. Is this process endo or exo? Endo. This process is endo, isn't it? Do you believe that bonds are stronger among and between water molecules in solid water than they are in liquid water? If you think the bonds are stronger among and between water molecules in liquid water than they are in solid water, which means hydrogen bonding is stronger, because those are the bonds among and between the water molecules, the principal bonds. If you think the bonds are stronger in the water liquid, then diving into a pool of ice cubes should be fun, gentle, easy. Well, if you think that's the case, go to your swimming pool, have the people that own the swimming pool take out all the water liquid and fill it up with ice cubes. Now do a belly smasher off the diving board and see how you feel after this belly smasher. Will you be happy and comfortable? Will you glide nicely through this pool of ice cubes? Or will you get hurt? Because the damn bonds are stronger in the water ice cubes than they are in the water liquid. So this thing is endo. Yet under these conditions it is spontaneous, this transformation. Well, why is it going? The change in enthalpy for this is against it. The change in enthalpy says, no, this shouldn't happen. Yet it goes. Proof? Not criterion for thermodynamic spont. The criterion for thermodynamic spont comes from the second law of thermodynamics, which is related arithmetically to delta G. The relationship is in the notes. You're not responsible for the relationship. But let's take a brief peek at the second law, which says the change in entropy for the universe is favorable, positive. For every spontaneous process. So notice the difference in sign convention. Exo, change in energy is minus, because the system is liberating the energy. But that's a favorable change from a change in enthalpy standpoint. But for a favorable change in entropy, plus for every spontaneous process, and the change in entropy for the universe for every process, any process, is equal to, no need this here, the change in entropy for the system plus the change in entropy for the surroundings. System surroundings. So let's take a look at this. Back to water liquid, but this time we're going to put it in the freezer at minus 10 centigrade, 1 atmosphere. So this time we're going to get the ice cubes. This time this is spun. But note, we've stipulated this as being the criterion for thermodynamic spontaneity. And if I have converted liquid to solid, is that a change proceeding with a favorable change in entropy? Yes or no? No. Change in entropy is not favorable for this. Yet it happened. Yet it's spontaneous. Well, then it must be true. If the second law is true, this condition must be met. For water, liquid becoming water solid in the freezer. Well, let's take a look how this condition is met. For the change in entropy, for a phase change, there's the relationship. The change in enthalpy, the change in entropy is equal to the change in enthalpy for the phase change divided by the temperature at which the change occurred. So let's imagine that we have studied this process with 18.0 grams of water. Does that quantity of water sound familiar? Remember the formula mass of water? What's formula mass of water? 18.0 grams, isn't it? So that's a mole of water, right? So we're looking here at the change in enthalpy, the heat, which has got to be liberated by a mole of water liquid in order for it to become a mole of water solid. So I've written over here, since water liquid becoming water solid is exothermic, this energy quantity corresponding to change in enthalpy is a minus number. That's an exothermic process. Which means, as water liquid becomes water solid in the freezer, the change in enthalpy the change in entropy, the change in entropy for our system is plus or minus. This is our system. Plus or minus. This is a minus number, right? Because the process is exo. So this is not favorable. Well, then let's take a look at this part of the puzzle. Because the same relationship applies, and the same quantity of heat is involved, because as water liquid 1 mole became water solid 1 mole, the enthalpy, the change in enthalpy for this process was liberated to the freezer compartment. That energy went into the air atmosphere of the freezer compartment. So the air atmosphere of the freezer compartment absorbed this energy, didn't it? The water liquid lost the energy as it went to water solid, giving that to the environment known as the freezer, the surroundings. Now tell me, we get the same energy up here, except now it's got a plus sign, because the energy was absorbed by the environment known as the freezer. That's a plus. That's endo. It absorbed the energy. And at what temperature did this freezer absorb this energy? At what temperature did the freezer absorb the energy? I'm listening. What's the temperature at which the freezer absorbed the energy? 263 K, isn't it? Minus 10 centigrade. At what temperature did the water liquid lose the energy? What temperature? At what temperature did the water liquid lose the energy? If you put a thermometer in this stuff as it freezes, there's my $64,000 Van Gogh picture of a thermometer. It's sticking in the water liquid. What temperature are we going to observe as this stuff becomes this stuff in the freezer? What temperature will we see? 273 K, won't we? So for the exo part of this transformation, I've got an energy quantity divided by 273. And for the endo part of this transformation, I got the same energy quantity, but divided by 263. Which is the bigger number? This one, isn't it? And if I put those numbers in here, am I going to get a positive delta S universe? You're damn right. Showing how the second law upholds itself as a criterion for thermodynamic spontaneity. All right, now more on this funny thing called entropy. Energy units, units, S. Joules per K-mole if we talk about molar entropy. Or mole K, who cares? My question is, have you seen these energy units before? Have you seen this collection of energy units before? The answer is you did in 2045. What property of matter did you study in 2045 on the chapter on thermochemistry which has those units? I'm listening. What is it? Molar heat capacity. That's it. So you think there's a relationship between molar heat capacity and entropy? You're damn right. Now, I'm not going to go into the difference. They are rather subtle. But the units are the same. But heat capacity on a mole basis, is the amount of heat that you need to put into a mole of substance to get its temperature to go up 1 degree centigrade. Or take away from the mole of substance to get its temperature to go down 1 degree centigrade. Whereas entropy is a measure of the ability of the substance to distribute its internal energy, which we've already reminded ourselves is most effective for the substance in its vapor phase. So back to S0. What does it depend on? Formula mass. This fancy squiggle is the symbol usually used for formula mass in textbooks, but I can't draw this too well on the board. So I usually use FM for formula mass. But this molar mass, formula mass, same thing. Phase. Temperature. The higher the temperature, the higher the entropy of a substance. The higher the formula mass, the higher the entropy of the substance. Phase, we've already talked about. Lowest entropy for a substance, solid phase, highest vapor phase. And then structure. So let's take a look at the structural aspects of entropy, at least in brief. You remember in 2045 laboratory on Tinker Toys? Remember playing with Tinker Toys? Molecular models? I call them Tinker Toys. Okay? You play with Tinker Toys in assignment 6. And regardless of what went on in lecture class, I insist on you learning about structural aspects of material like isomers. In 2045, did you hear about isomers? Because I know you heard about isomers in 2045L. Hydrocarbon isomers. C5H12, is that a hydrocarbon? What's a hydrocarbon? By definition, what is a hydrocarbon? You think hydrocarbons are common materials? You betcha. There are compounds composed strictly of carbon and hydrogen. Or hydrogen and carbon if you prefer. Hydrocarbon. Nothing fancy about that. Did you learn the rules of the road for developing Lewis structures for hydrocarbons? We asked you to pay attention to this in 2045 lab. We reminded you, among other things, that carbon in an even electron hydrocarbon. What's this even electron mean? If I use this language, you don't know what it means, then you're not knowing at all what I'm talking about. Even electron, what's that mean? Well, if you're going to write a Lewis structure for any material, what's the thing you do first? What do you do first? Count valence electrons. Okay, C5H12, let's count them. 5 times 4 is 20, plus the hard part. 12. That's 32, isn't it? So for C5H12, I got 32 dots. Each dot's an electron. Is this an even number? Yeah. So this is an even electron hydrocarbon. Right? Even electron means even number. The electron counts an even number. Wholly divisible by 2. Okay? We reminded you that in all such hydrocarbons, with practically speaking no exceptions, so we'll consider there are no exceptions, each and every carbon atom is part and parcel of a valence electron structure, which has how many bonds? 4, you betcha. That's really important, because just about even electron carbon containing molecule has carbon in a 4-bond environment. You hardly ever find carbon with any non-bonding electron pairs. You will for novel species like carbanions and things like that. We're going to talk about those now. Those are very reactive. They're not very stable. So for stable carbon-containing molecules which are even electron, the carbon is always in a 4-bond environment. 4 bonds. Well, what can these 4 bonds be? Can I have 4 single bonds? 4 single bonds? 4 sigma bonds? I can have 4 sigma bonds. Then the carbon is how hybridized? sp3. What if the carbon is sp2 hybridized? Then how many single bonds do I have? 3. And how many double bonds? 1. So, for that, I got 3 sigma bonds, the sp2 carbon, 3 sigma bonds and 1 pi bond. Okay? What if the carbon's sp? Two sigma bonds, 2 pi bonds. Right. Or it can be a sigma bond, a single bond, pardon me, it could be a single bond or a triple bond. Right? Well, it's always 4 bonds. So this gives us a lot of information regarding trying to write structures for carbon-containing molecules. We're always looking for 4 bonds for each carbon. If in an even electron carbon-containing species, and just about every carbon-containing species is a stable even electron species. Now then, C5H12, 32 electrons. Since there won't be any unpaired electrons in this thing, I'll divide by 2 to let me know there's going to be 16 bonds in this picture. 16 shared electron pairs. And 12 of these electron pairs are going to be used to do what? See that formula, C5H12? 12 of these electron pairs are going to be used for what purpose? connecting hydrogen to the carbon skeleton. So how many bonds does it leave me? 4. So without doing anything fancy, if I'm going to write Lewis structures for this thing, I know that each and every Lewis structure which is acceptable for the formula C5H12 has got 4 carbon-carbon bonds. There's one of them. Here's a model. That so-called straight chain hydrocarbon is hardly a straight chain molecule. But when you draw it on a board, it looks like straight chain, doesn't it? But every one of these carbons, I ran out of black parts, so I got a yellow part in the middle. Who cares? Okay? 4 of these, all 5 of these carbons are sp3 hybridized. And the general geometry with an sp3 hybridized atom, when it's got 4 sigma bonds connected to it, is tetrahedral. You see a tetrahedral arrangement of immediately connected atoms to any individual carbon atom? It's all tetrahedral. So this thing is hardly straight chain. Now I want you to look at this, and then I want you to look at this other material, where the longest carbon chain is 3 carbon atoms long. Do you see that's also a C5H12 molecule? Okay? I'm going to make that molecule right now. And then we're going to ask a question. Here's this molecule. Which one has the higher entropy? This one? Or the one we had before? Model. Rubber band. 2 rubber bands tied together. Look at all these things this rubber band can do. Wiggle around, jump around, all kinds of things it can do. Now I'm going to take this rubber band, the 2 rubber bands, and I want to make some knots in it. Same 2 rubber bands. Except that I am restricting severely the ability of these 2 rubber bands tied together to move around in space. Can this thing wiggle around as much as it was able to before?
No.
So which version of the rubber bands has the higher entropy? The tied up version or the untied version? The untied version, because it can wiggle along a much longer direction and distribute internal energy much more effectively, which is why that version of the hydrocarbon has got the much higher entropy. We'll pick it up from this point next time.